Welcome back to the second video on section 4.6, change of basis. In this video, I'm going to show you a computational example on how to compute the transition matrix and how we use the transition matrix to compute the coordinates of a vectors, but relative to different bases. So let's look at this vector space V consists of all the 2x2 matrices that looks like this. By now, you should be able to verify that V is actually a vector subspace of the vector space M2x2, and therefore itself is a vector space. And also by now, you should be immediately realize that this vector space V has dimension 3. You also should be able to tell what are the standard bases. But instead of working with the standard bases, we are given two different bases, B and C. So the B1, this vectors here, is a 2x2 matrix, of this form, and you have B2, you have B3, so we have three different vectors. Our vectors in this case is a 2x2 matrix. So these are the vectors for this basis B. These are the vectors for this basis C. First thing we want to do is to compute the transition matrix from basis B to C. So from the first video, we know how to do that. We take the vectors, first vectors from the basis B, but instead of putting the vectors, we're not putting the vectors here. The vectors here will be, if you put the vectors, it's going to be a 2x2 matrix. So we're not going to do that. We are going to put the coordinates of that vectors relative to the basis C. So this is going to go into the first column of this transition matrix. The second column of the transition matrix is going to be the vectors B2. Again, not the vectors B2, but the coordinates of vectors B2 relative to the basis C. And on the third column, you are going to put the vectors B3, not the vectors B3, but the coordinates of vectors B3 relative to basis C. That's how we construct the transition matrix from B to C. So how do we find the coordinates? So according to the definitions, if you want to find the coordinates of B1 relative to basis C, you will have to find the coefficient K1, K2, K3 such that K1C1 plus K2C2 plus K3C3 will equals to your B1. This is a very simple example in this case because it turns out that our C1 and B1 are the same. So you can set K1 equal to 1 and then turn off these two matrices by setting K2 and K3 equal to 0. So because our K1, K2, K3 is 1, 0, 0, therefore the coordinates of this matrix relative to the basis C is nothing but 1, 0, 0, 1, 0, 0. Okay, 1, 0, 0. So from here, we can see that in order to compute this coordinate, B2 relative to basis C, and also the coordinate of vectors B3 relative to basis C, we basically have to repeat that computations twice, two more times. So it's going to look something like this. So you have your B2, okay? You want to find your K1, K2, and K3 such that you have this equation. We can do that. We can try to compute this, K1, K2, and K3, and then you change it to B3, and then you have to redo these computations to find what are the K1, K2, and K3. So instead of redoing all these things 3 different times for B1, B2, and B3, we can try to set up equations that can do all these computations. So instead of looking at all these B1, B2, and B3, suppose we pick a generic vectors V from this vector space. So it will look like A, B, C, and 0, right? So you want to find K1, K2, and K3. So the way to do it, it turns out it's going to be involved, right? It's going to be equivalent to solving this system of equations. So you take K first component, you have K1, K2, K3, add up has to be equals to A. Look at the second component, you pick up the second equation, and then look at the third component here, you pick up these equations. So in order to find K1, K2, and K3, it is equivalent to solving this system of equations. And you can also put in augmented matrix. And then the rest is a very typical computations that we have. So let's go back to the B1. So because we call this A, B, and C in the previous setup, so our A, B, and C are 1, 1, 1. So you put the system here, 1, 1, 1, row reduce it to the identity matrix. So immediately you can see K1 is 1, K2 is 0, K3 is 0. That's the reason why you have the 1, 0, 0. And if you put A, B, C as 0, 2, 2, ABC 0 to 2 because we call this ABC. Okay, so 0 to 2, row reduce it, and you will have K1 equals to 2, K2 is 0, K3 equals to -2. Therefore, the coordinate B2 relative to basis C is 2, 0, -2. So same thing here. You can do these computations. So our ABC in this case is 0, 0, 3. So you do these row reductions. You have K1 equals to 3, K2 equal to -3, and K3 is 0. So therefore, the coordinate is 3, -3, 0. So if you want to do it like 3 different computations, you can do that. So you can find the coordinates for all these vectors relative to the basis C. So we can put all of them together. All right, remember that this is what we want to do. We can put all of them together: 1, 0, 0, 2, 0, -2, 3, -3, 0. That's perfectly fine. But instead of do that computation 3 times, we can also just do it in one single computation. Okay, so how do we do that? Recall that in order to put so if you do these row reductions, you can see the coefficient matrix is the same, the coefficient matrix is the same, the coefficient matrix for all the previous 3 computations are the same. The only thing that is different is the ABC from 1, 1, 1 to 0, 2, 2 to 0, 0, 3, and then you row reduce it. So instead of row reducing it this way, we can put the 1, 1, 1 right here. Okay, and then put the 0, 2, 2 right here, and put the 0, 0, 3 right here, and do this row reduction 1 time. Now try to imagine what happened to this row reduction when we do this row reduction. This place here will be reduced to 1, 0, 0. Okay, this thing here will be reduced to 2, -2, 2, 0, -2, and then this place here 0, 0, 3 will row reduce to 3. Okay, -3, 0. Right? It's the same thing, right? So when you do these row reductions, the operation will operate on this and give you the operations will operate on this and give you this, okay, which is here. It will operate on this and give you this, which is here, and it will operate on this and give you this, which is here. So you can put all of this together and put it in a slightly bigger augmented matrix and row reduce it to the identity matrix, and that will be your coordinates for B1 relative to basis C, and coordinate for B2 relative basis C, so on and so forth. So indeed, this result right here is exactly the same as this. Therefore, your transition matrix from B to C is nothing but this, okay? It's exactly the same vectors. All right, I don't want you to memorize anything because you might get confused. So you just have to remember the very basic formulas to compute the transition matrix, which is this. You know that you have to compute all these coordinates. So when you try to compute these coordinates, you will know that you will have to solve this kind of system of linear equations. So in order to solve this system of equations, you will have to do it like this. But instead of doing it 3 times, you can put it together, and then you just have to do 1 row reduction instead of 3 row reductions. Obviously, it's completely fine if you do 3 row reductions. What I need is to get a coordinate. All right, so if you look for a slightly more efficient way, this is a slightly more efficient way. Now, once we have the transition matrix, we can do the following computations. So recall that right now we have the transition matrix. We know the transition matrix from basis B to C. So if you are given vectors from this vector space V, and you don't really know what that vectors is, but you know the coordinates of that vectors relative to basis B. And the question is, what is the coordinates of these vectors relative to basis C? Well, remember the formulas to compute these transitions is the coordinates of vectors A relative to C is related to the coordinates for vectors A relative to B in this way, right? So this is B transition matrix from B to C. So you put the coordinates from B, it will transition to C and give you these coordinates. And we already computed that. So this is the transition matrix. Put the coordinates here and do that computations, and immediately you get this result, which gives you the coordinates of these vectors A relative to basis C. Okay, this is what happens if you already have the transition matrix that looks like that. So any coordinate relative to basis B, you just have to put it inside here, multiply with this transition matrix, and immediately you have the coordinates for these particular vectors here. Suppose we are given instead of the coordinate relative to B, but now you have a vectors A, the coordinate relative to basis C. Okay, how do you get the coordinates of the vectors A relative to the basis B? So in this case, we will need this transition matrix because you are given AC and you want to find AB, so you better put this AC to the transition matrix which transition from C to B so that you can have B. The notation is pretty self-explanatory, so so you should know that this is how it works. And so instead of recalculate what is the transition matrix using the basis method, we also see in class that the transition matrix from C to B is actually the inverse of the transition matrix from B to C. So the inverse of transition matrix from B to C is the transition matrix from C to B. So we just need to compute the inverse of the matrix that we obtained before. So we can do it from row reductions. Put the transition matrix here, put the identity matrix here, and row reduce it to identity matrix. So this will be the inverse matrix of this original matrix right here. And from our theory, we know that this is exactly the transition matrix from C to B. So once you have that, you can put the coordinates of the vectors relative to basis C, and then you will get the coordinates for basis B, and it turns out it has to be 1, 1, 1 because this is exactly the same computation. It's the same example. So we have seen it before. So this is the 1, 1, 1s that give you this coordinate 6, -3, 2. So if you have this 6, -3, 2 as this coordinate with respect to basis C, if you want to change it back to B, it will have to be 1, 1, 1. So this verify all our computations. And final example is that suppose you are given a vectors, so in this case a matrix in that vector space. If you are asked to find a coordinate, okay, you're not giving a coordinate, but you're asked to find a coordinate, you don't really have to do it using transition matrix. You can't really do that. You can, but it's going to be long. So if they ask you what is the coordinate relative to a basis C, you just have to follow the definitions and figure out what is your K1, K2, and K3. If you really want to involve transition matrix, you will have to do it in multiple steps. That is going to be a little bit redundant, but suppose you want to do that, one way you can do it is to first find the coordinates relative to basis B, and then apply this and do all this computation, but this is not necessary. So if they ask you to find the coordinates, you've given a matrix, okay, of vectors in the vector space, and ask for the coordinates of relative to some basis, you can just do it from the definitions. The reason why, when do we actually use a transition matrix? We use a transition matrix when they give you the coordinates. So if they give you the coordinates and you want to know the coordinates are relative to the other basis, then you can do it easily with the transition matrix. You can actually also just compute it through the definitions, but if you already have the transition matrix, this is how you apply the transition matrix. And that's the end of this long videos.